In this video, we're talking about the ACT category of geometry, and we have the topics which are included here as trig identities, and then we're going to talk about the law of sines and the law of cosines and how you may see these on the ACT. Let's remember that an identity is an equation that is always true. It's something that we can always count on. And there are several different trig identities and relationships, but we have a few that we commonly see on the ACT and therefore are important for us to review and even memorize at times. So here's the ones that are going to be important for the ACT and what we're looking at here. When we look at the first ones on the left-hand side, we have some relationships that are in the equation form for sine squared x plus cosine squared equals 1. I would say this is the number one identity that you probably need to be familiar with that we've seen most often is that one. Sine squared x plus cosine squared x equals 1. We also have the relationship of secant and tangent, cosecant and cotangent. Cosecant x is equals 1 over sine x. Cotangent x is 1 over tangent x, and secant x equals 1 over cosine x. So knowing these enough that you can apply and use as needed, but honestly, the sine squared x plus cosine squared x equals 1 is really the one that if you had to say one that you needed to commit to memory, I would say that one. The others be familiar with and be able to apply as needed. Knowing these identities are going to be able to help you to simplify and even solve some equations, expressions, and be able to get them into a form that we're looking for with our answer choices. So that's really the identities that we need to be aware of, in addition to remembering our definitions of sine, cosine, and tangent that we talked about on a previous video. Now, looking at the law of sines, we have some relationships that we can use with our angles when we know that we have a right triangle. And that's what we can use when we can make use of our sine, cosine, and tangent functions. We can even make use of the Pythagorean theorem. But what about when we don't necessarily have a right triangle? This is where we're going to make use of the law of sines and the law of cosines. And it gives us this relationship where we can still possibly find angles of the triangle and lengths as well. We have this relationship that's given by the law of sines where we have the sine of angle A over side length A is equal to sine of angle B over side length B equal to the sine of angle C side length C. And that's given this triangle that we have defined here on the right where, for example, angle C has side length C opposite of it. And when we do this, we can use this relationship here of law of sines. Let's say we're given an angle and its opposite side length and maybe another side length. We can find the angle opposite of that, one that we don't have, using this relationship here. So when you're given the question or example or whatever, make sure that you line up your angles and your side lengths so that they will fit similar to our example that we have here, mainly that you're getting the side lengths and the angles opposite of one another. Now again, this can be used for any triangle, not just right triangles, and that's what makes it special. A lot of times when you'll see the problem begin to be set up this way, recently they have been giving this relationship of sine A over A, sine B over B, sine C over C, but they may not always give it. So I still think it's enough that you should be familiar with this, but a lot of times they're giving it to us. Make sure you remember this is for the law of sines. Now you can also use the reciprocal of this relationship. On the previous slide we had sine A in the numerator and side length A in the denominator. Well, we can flip that if we need to. It's fine because it's a relationship here, and as long as we set these proportions up the same and we put all the side lengths in the numerator and all the sine functions in the denominator, just be consistent. You can use it that way as well. And use whatever portion of the relationship you need for your unknowns. If we're not concerned with angle C and side length C, if we don't have those, if they're not given, but we do have portions of A and B and we're still looking for one of the other unknowns, all you have to do is set up what you need to use for the law of sines. So again, we're using sine with this law, but we also have the law of cosines. And when we have the law of cosines, we've got, again, this relationship, same triangle that is set up as it was previously. And when we make use of this law of cosines, it's again for triangles that are not necessarily right triangles. If we have a right triangle, we're going to use the Pythagorean theorem. But when we don't, we can make use of this equation here, this relationship. This time we're, in this case, looking for c squared, and we say that that's equal to a squared plus b squared, the two other side lengths, minus 2ab cosine of c. A lot of times the ACT gives us some form of this equation, but not always. So I always encourage you to be very familiar with what we use. When we're looking for the unknown of side length C, if you can remember that that's always going to be equal to the square of the other two sides, summed together, and from that we subtract 2 times AB times cosine of the C, the one that we're unknown. You can rearrange this formula to solve for any other side lengths. Here we're solving for a squared instead of c squared. And notice how we just changed out the other two side lengths and the angle measure in our cosine function. We can also solve for b squared. Again, we're changing out side lengths and angle that we're looking for. The other thing to be familiar with is you may be asked to find, for example, if we've got the c squared equation, you may be asked to find angle C, and you could do that by just moving everything else to the opposite side of the cosine C, and then you would take cosine inverse to find angle measure C, or A or B, whichever one we're looking for. We just want to be able to make use of this formula given whatever unknown we're looking for. And I just wanted to reiterate again, in the past ACTs, we've been given these relationships mostly for sine and cosine, either stated in words or given in formulas, but that's no guarantee that they'll give it to us in the future. So just be familiar with these relationships and then how you can apply each of them. Let's take a look at an ACT type example. Pause the video here and we'll come back together and work this. The question says, what is the measure of angle A to the nearest tenth? So we're looking for the measure of angle A. We need to make an observation or two. First of all, we have no indication that this is a right triangle. We cannot base it alone on what it looks like, that maybe it looks like a 90 degree. And so we can't just use sine, cosine, or tangent or use the Pythagorean theorem, but we can use some applications. We are given 3 side lengths, the 6, 7, and 10. Based on that, it's usually an easier thing to do and works better that we can use the law of cosines, because here we have 3 side lengths and we're looking for angle A, so we can get that angle A by itself by plugging all the other values in for the side lengths A, B, and C. And we're going to do that here. We reorganized the equation so that now we're solving for A, and we're going to do an inverse cosine, plugging in our numbers that we have for A, B, and C, and we'll find that A is equal to 43.5. Now we're going to have to use our calculator here to do the cosine inverse of that 0.725, and that's where we get 43.5 degrees, which is answer choice B.